Hey, good morning, everybody. This is our last lesson in Unit 4. We're looking at modeling with trigonometry today. In this last lesson, we're going to put our knowledge of trigonometry to work on solving some practical applications. First, let me remind you about angles of elevation and angles of depression. An angle of elevation is the angle through which your eye moves in an upward fashion from the horizontal to look at something above you. So you've got to first consider the straight line out from your eyesight, and when you look up, that line of sight is called the angle of elevation. And in the opposite direction, when you're riding in an airplane, you look out straight on the horizontal, and when you look down at something, that movement downward from the horizontal is called the angle of depression. So let's try a few of these. Let's say the angle of depression from the top of the Ponce Inlet Lighthouse is 170 feet above the surface of the water, and that angle of elevation is 5 degrees. So we know that this angle right here between the water is 5 degrees, and that the lighthouse itself is 170 feet in height. So we're looking for this distance from the buoy to the lighthouse. We're going to call that x. And we're also making the assumption that this forms a right triangle and that this lighthouse is perpendicular to the ground level. So we've got a right triangle there. And by setting up that ratio that way, we can use the tangent of the angle, which is the opposite side divided by the adjacent side, because we have those missing features that will give us the adjacent side. So we're given that the angle theta is 5 degrees and the opposite side is the height of the lighthouse, that's 170 feet, and we don't know the x value. So we can solve for x by using our calculator and dividing 170 by the tangent of 5 degrees. So I'm going to use my Inspire here, and I can substitute in tangent of 5 and change that to a degree and put a decimal there. It'll give us a decimal amount. So 1943.11. So the distance, the buoy, is about 1943.11 feet from the lighthouse, the buoy's distance. Okay? Here's another one that's using the Statue of Liberty. So the Statue of Liberty stands on a 150-foot high pedestal. So from this base here, this is 150 feet tall. And we want to know the height of the statue itself from the bottom of the base to the top of the torch there. And what else do we know? If we're standing out here 280 feet away from the Statue of Liberty, and we have this right triangle here, and that the angle of the elevation, so that would be our eye is down here and we're looking up from the horizontal, this angle is 47 degrees. So we can find the height of the Statue of Liberty itself by using, again, the tangent of 47 is the height plus the pedestal divided by the 280 feet that we're standing away. So using our calculator, 280 times tangent of 47 is going to be the height plus 150. So we'll go calculate that. 280 times the tangent of 47 degrees is about 300.263. So if this is 300.263 and we subtract 150 from that, then the height is going to be roughly 150.263 feet high. So if we rounded that height we could say that the statue is about, S-T-A-T-U-E, statue is about 150 feet tall. So the base, the pedestal, is 150, and the statue itself is 150. And if you've ever been there, you know that proportion is pretty close to true. In example 3, suppose we have a 50-foot extension ladder, and it's leaning against the side of a 2-story house. So this is going to be my 2-story house. We've got a 50-foot extension ladder leaning against the side of that house. And the base here of the ladder is 6 feet from the base of the house. So you can see that right triangle proportion here. So from the base out to the edge of the ladder. And we want to find the angle that's formed by the ladder and the house. So here's the angle that's formed by the ladder and the house. So that would be this angle up here, I would guess, right? So let's see, what do we have? We have opposite and hypotenuse. So that sounds like the sine to me. So if we set up that proportion that the sine of the angle is opposite to hypotenuse, then we're going to see that the sine is 6 divided by 50. And using the inverse properties, then the angle theta would be found by sine inverse of 6 over 50. So jumping over to our calculator, you can see here that the sine inverse of 6 over 50 is about 0.120 radian. And if we convert that 0.120 radian to a degree, we'll find out that the angle up there at the house and the ladder is about 6.9 degrees. So let's see, we were going to record that. This is about 0.129 or 6.9 degrees. And they're asking us, would you feel safe climbing the ladder if this angle up here is 6.9 degrees? That's a tiny little angle. And if that angle is 6.9 degrees, then this angle down here is going to be about, 83 degrees? I would say not such a good idea to climb a ladder. That's way too steep of an angle. It's almost straight up and down against the house. So not a good plan to climb that ladder. Here in example 4, the angle of elevation of the top of the TV antenna mounted on top of the Eiffel Tower is measured to be about 80 degrees, 1 minute, 12 seconds. So first we know we're going to have to convert 80 degrees, 1 minute, and 12 seconds. And I've already pre-done that and got 80 degrees and 80.200ths of a degree. So that is this angle of elevation they're telling us. So this is 80.02 decimal degrees. And if we're standing at a point that's 185 feet from the base of the tower, we want to know how tall the tower plus the TV antenna is. So that would be this vertical height here, right? So I'm looking for that height there because we're 185 feet away from the base of the tower. So we could figure that out by using tangent again. Tangent of 80.02 decimal degrees is the height divided by 185, opposite to adjacent. So with our calculator, 185 times tangent of 80.02, see what that is. 185 times the tangent, went too far, of 80.02 decimal degrees is about 1,051.33 feet. So 1,051.33 feet is the height of the tower plus the TV antenna. And I believe last year one of my students did a Google search and found out that the antenna from their search, that antenna was about 4.3 meters tall, which is roughly 14 feet, which makes the tower 1,037 feet tall, plus the antenna for the 1,051 feet. And you could research that on your own and find out the truth of that fact. Okay, let's look at this next example. I've got a dual screen here. So a passenger in an airplane is flying at an altitude of 9 kilometers, and they see 2 towns directly to the east of the airplane. So this height here is 9. The angles of depression to the towns are 22 degrees, so that would be this angle, 22 degrees, and 46 degrees respectively. So 46 degrees is this larger angle, 46 degrees. How far apart are the towns to the nearest kilometer? So let's say we had this distance from here to here. That's our whole distance. And we want to find this distance here. We're looking for that. Okay, so we got this total distance, and well, I don't want to use D. Let's say this is X. So if this is X, we'll call this distance here Y, and this distance between the 2 towns would be X minus Y. So one thing I want to point out, if this is 9 kilometers tall, we're making 2 right triangles, and I see 2 parallel lines, the ground and the line of sight, cut by a transversal here. So if you're considering this smaller triangle here, and this is 46 degrees, then the 2 parallel lines cut by this transversal makes this angle down here 46 degrees, right? So that angle down here is 46 degrees, which makes this angle up here 44 degrees. And the height is 9 kilometers. We've made a right triangle, and that's the distance Y on the ground between the airplane and the first town. Now the second triangle still has the same height, 9 kilometers, and we've got 22 degrees for that angle of depression, which makes 2 parallel lines cut by a transversal, so alternate interior angles are equal, and this angle down here at the ground is 22 degrees as well, which makes this angle up here 68 degrees. So that gives us the height for the airplane all the way out to the second town, which is X. So we've got 2 triangles to resolve. And I can resolve this first one either using opposite to adjacent or opposite to adjacent. I happen to like the 44 degrees because it puts my variable in the numerator. So let's approach it that way. Let me get out of this dual screen view here and just get to one page now. So using that top angle, the tangent of 44 degrees is 9 divided by Y. I'm sorry, I said it put my variable in the top and I'm writing it in the bottom. Is Y divided by 9. So on my calculator, 9 times tangent of 44 degrees. If you calculate that with me, I get 8.69 kilometers for that distance Y. And then this one the same way, if we use the 68 degrees, opposite is in the numerator and adjacent is in the denominator. So tangent of 68 degrees is X over 9. So X is 9 tangent 68 degrees. That's roughly 22.28 kilometers. And our problem was to resolve the distance between the 2 towns. So that was, let's look back now, that was X minus Y. So the distance between the 2 towns is X minus Y. The distance is X minus Y, which is 22.28 minus 8.69. So those two towns are roughly 13.59 kilometers apart when the passenger looked out the window. That's a calculation to figure the next time you fly in an airplane. I think I'll pass and watch the movie. Okay, let's go look at some navigation problems. So using trig and navigation, if a U.S. Coast Guard patrol leaves Port Canaveral and averages 35 knots, that's a nautical mile per hour, for 2 hours on a course of 34 degrees, and then 3 hours on a course of 124 degrees, we want to know what the boat's bearing and distance from Port Canaveral is going to be. So first, I've got to figure out, let's see what's on the next page. Oh, our markings. Okay, so first I got to figure out if the bearing here is 34 degrees, and we've gone 35 knots for 2 hours, then the leg from here to here is going to be 70 nautical miles. And then we turn and go 124 degrees, which puts this angle in here. That angle in there is going to be 56 degrees. And if this is 34 degrees, 2 vertical lines cut by a transversal makes that angle in there 34 degrees. And 56 plus 34 makes angle B a 90-degree angle. Now, for 3 hours, we go at the same rate, 35 knots. So this leg is 105 nautical miles. And what do we know about this one? If this is 34, let's see, first we've got to resolve that triangle, don't we? So let's go to the next slide. We've got this is 70. We don't know this angle yet. We knew that this was a 90-degree triangle here, and that this leg was 105. So we're trying to find out where that ended up. That's not a very good picture here. We could do better than that. That makes it look a little bit better. So we went 70 nautical miles here. We found out this was a 90-degree angle in here. We knew this was 105 nautical miles over here to C, and we want to find out that triangle. So if we solve for ABC, then we know that AC, if this is A, and this is B, and this is C, we can find out that AC is the square root of 70 squared plus 105 squared. So let's go calculate that. We want the square root of 70 squared plus 105 squared. Whoop! That didn't go too well. Let's try that again. The square root of 70 squared plus 105 squared is about 126.194. So this side is 126.2 nautical miles. So roughly 126.194 nautical miles. So find the length of AC, and then we can find the angle theta for the bearing. So the tangent of theta, we want to know what theta is. The tangent of theta is opposite to adjacent. So calculate that. Tangent inverse is opposite divided by adjacent. And we're going to convert that to a degree. So 0.98 radians times 180 divided by pi is roughly 56.31 degrees. So theta is 56.31 degrees. So theta is roughly 56.31 degrees. And to find the bearing, you know, this angle was 34 degrees. Let's go look. So the bearing goes off the north. We're going 34 degrees first. So our bearing is going to be 34 degrees plus another 56.31 degrees. So our bearing would be 90.31 degrees north of east at a distance of about 126 nautical miles. So they have 126 nautical miles if A is Port Canaveral out to the boat at sea. Okay, so using navigation in a different way, this time we're going to have a park ranger spots a fire from a 125-foot tower in the Great Smoky Mountains. And the angle of depression is measured to be 1 degree and 20 minutes. And we want to find the distance to the tower, to the fire from the tower in feet, and then convert it to measurement in miles. Something happened to the screen there. So the 1 degree, 20 minutes is 4/3 of a degree. And that's our theta angle. So the picture here, if you have a fire here, and we're looking from the horizontal, this is our tower. We're at the top of the tower. This is our tower. It's 125 feet tall. We're looking through this angle, and it's 1.33 repeating degrees, which makes this angle down at the bottom 1.33 degrees, right? And we're looking for the distance, and we're assuming that's also a 90-degree triangle. So the tangent of our 1.3 repeating degrees is opposite to adjacent. So the distance is 125, and if we divide by tangent, that's the same thing as multiplying by cotangent, 1.3 degrees. So let's go calculate that. And then we've got to convert this answer to how much of a mile. Let's see. So we got 125 cotangent of 1.3 repeating, not a comma, degree, which is 5371.85. So we've got roughly 5371.85 feet. And I'm multiplying that by the conversion factor that 1 mile can be converted to 5,280 feet. So the feet would cancel. So 5371.85 divided by 5,280 feet gives us a little more, 1.017 of a mile. So that fire is roughly, we're looking at that fire, and that fire is roughly 1.017 miles away from the tower in the Great Smoky Mountains. And then our last type of practical application is going to be simple harmonic motion. An object moves on a coordinate axis is in simple harmonic motion if its distance from the origin D at any time t is given either by the cosine times omega t or the sine times omega t. The motion has an amplitude a in the maximum displacement of the object from its rest position. So if the function is cosine, that's being pulled up or down. But if it's sine, that's starting at rest or at zero or at the origin. And the period of the motion is still 2 pi over the b value, but here our b value is the Greek letter omega, where omega is a positive number. And the period gives the time it takes for the motion to go through a complete cycle. And if we want to know the frequency, that would be omega divided by 2 pi. And the frequency tells us the number of oscillations for our unit of time. So we'll start out really simple. Let's say we have a point on the tip of a tuning fork, vibrates in harmonic motion described by the equation d equals 12 sine omega t, where omega for a tuning fork has a frequency of 386 vibrations per second. So we know that the frequency was given to be omega over 2 pi, and they told us the frequency was 386 vibrations per second. So if we want to know omega, then omega is 772 pi vibrations per second if we're answering in radians. And next, a ball on a spring is pulled 6 inches below its rest position. So that tells me right away that we want to use cosine. We'll use the cosine formula since the ball is going to be pulled from rest, and rest is the origin. Use cosine since the ball is pulled from rest. And we said rest is the origin. And it's pulled in a downward motion, pulled downward to start. So we know that to begin with. And the period for the motion is 4 seconds. So that means we know 2 pi over omega is 4. So omega is 4 divided by, or omega is 2 pi divided by 4, or pi over 2. And we want to write the equation for the ball's simple harmonic motion. So the third step we would do, we also know that it was pulled 6 inches below. So A is going to be -6 if it's pulled down. So our equation that's going to model this is D equals A cosine omega times time. And our A value is -6. The function to model it is cosine. Omega is pi over 2 times time. So we wrote an equation that would model simple harmonic motion for a ball on a spring pulled 6 inches down from rest with a 4-second long period. And then our last example, let's say we have a mass that's oscillating up and down on the bottom of a spring, assuming perfect elasticity and no friction or air resistance, and it can be modeled as harmonic motion. If the weight is displaced a maximum of 4 centimeters, we want to find the modeling equation if it takes 3 seconds to complete one cycle and assume the object starts at rest. So which model will we use if the object starts at rest? When t is 0, we're at the origin. So we're going to use the sine model. We're going to use sine to model it. And the maximum displacement is 4. If the maximum displacement is 4, then A is 4. And the period is 3 seconds. So if the period is 3 seconds, the frequency is, I can't spell frequency. The frequency is 1 cycle every 3 seconds. The frequency is 1/3. So we know we've got to find W, so 2 pi over W is 3. That makes omega 2 pi over 3. So working through this kind of thought process, we can write the model using the sine curve, which would be displacement is 4 sine 2 pi over 3 times time. And we have written a model for harmonic motion on a spring. And that's the end of chapter 4. I'll see you on the other side of the test. Good luck.